In the next two videos, we will be talking about measurement error problems in our dependent and independent variables. This particular video is going to focus on the measurement error in our dependent variable. Okay, now it could be the case that we cannot collect data on the variable that we are truly interested in, but because we are interested in some sort of a question, we are only able to collect, let's say, data from surveys where the data could suffer from measurement error problems. So let's take an example and understand this. So let's first generally write out the model. Maybe we're interested in the following population regression model, where our dependent variable y star is unobserved. Okay. So we have a random sample on all our x's, but we do not directly observe y star. Okay, an example could just be that y star is actual family savings for a year. Okay, and the best we can do is just gather this information through through the amount that is reported by each family in some survey. So let's say we observe what they are saying in the survey, but not what is the actual saving. Okay, so there could be people underreporting their saving or overreporting their saving. So there could be some under or over reporting that's going on. Okay, and this happens also, if you think about, unemployment rates, people misreport their job status, right? They would, or employment status, they would say they are employed typically because this is a matter of prestige, and that would, not give you the correct picture when it comes to unemployment rates. Or it would underestimate the unemployment rates because people are just trying to save face by saying they're employed, but that doesn't really help economic policy. Anyway, going back to this example of this is y star, actual family saving, but what we're getting is just what they're reporting in surveys. What we would like to do is we would like to regress actual savings, right? We want to understand what determines actual saving rates, but what we can do, the best we can do is regress what they reported in the survey on family savings, right? On all the X's. So the question for us is, suppose that the model with y star actually satisfies all the the Gauss-Markov assumptions, at least the first four. We want to understand under what assumptions does mismeasurement of this dependent variable not cause bias in OLS. So let's try to understand this, and let's say that we can come up with like this simple measurement error. Maybe there is some kind of misreporting going on. Somebody's overreporting, some families are underreporting, and there's actually some difference E naught between what we observe. Let's see, what we observe, let's say in surveys, and what is unobserved. So maybe there is some, this is again like a theoretical concept here, but basically we're saying that there's some sort of a gap, right? So we can rewrite this equation in terms of y, which is observed. So we can say y is equal to y star plus E naught, right? And each E is going to be different for each family. Sometimes E is positive, sometimes E is negative. And so what we can do is, instead of y star, we can plug in, once we plug in what is y, then we are going to get this composite error in the end, right? So E naught is going to be just added to the former error term. So what happens is that the measurement error E naught becomes a part of the composite error term on the right hand side. And so under the Gauss-Markov assumptions, for the original model, we said that, if those are satisfied, u is going to be uncorrelated with the x's. And if we add the assumption that E naught is also uncorrelated with each of those x's, then we are okay, right? So the key assumption for OLS to be consistent when y has or our dependent variable has a measurement error is that the measurement error E naught is uncorrelated with all the x's, right? So this is the condition that we are thinking about, okay? Now, along with the traditional assumption, we also know that the expected value of E naught should be 0. What happens is that it is usually assumed that the covariance between, or the correlation between U and E naught is 0, which basically implies that the variance, when we look at the variance of this composite error term, the variance of this composite error term is going to be greater than the variance of U, which was sigma square U, right? So now, because we have this measurement error, the variability in our errors is going to be higher, okay, than the previous case where we only had U. So in other words, measurement error in Y increases the error variance, but this is not something we need to worry about too much, because if we could collect data on Y star, we would have collected that already. We can only collect data on Y, and so that just means that there's a trade-off. We just got to tolerate this higher error variance. Okay, so if x1 is income, right, if one of the variables that affect savings, this is household savings, and we are saying that the savings are dependent on income, then, you want to think about, questions like, what if people with higher incomes are more likely to overestimate their saving, right? Then you would have the case that E naught is going to be positively correlated with X1. So we're saying that what would be the correlation between income, which is our X1, and this measurement error, okay, in the way we defined it. Okay, so we're basically saying that, what is the sign of it? Is it positive? Is it negative? What is it, right? So you want to think about these cases.